Okay, so let's share my screen. Everybody, can you see the homework set 1?
Yes.
Okay, great. Uh, hey Jared, so what's your question?
Yeah, so the first one I was having a lot of trouble with was problem 2, and problem 3, and I started on problem 4. I feel like I could do that, and I haven't looked at problem 5 and 6.
Okay, so so number 6, I mean, as of your current knowledge, I mean,
Well,
uh, so far, excuse me, I mean, so far what we discussed until the last class, you are able to solve like 1 through 5, but number 6 is the different problem. Today I will be discussing something similar. So, and then for example, for number 2 and then number 4 and many other problems on through 5, if you just listen today's lecture, then you will be able to solve. And but it's still, even without today's class, whatever we discussed until last class, you would be able to solve 1 through 5. Yeah, but if you listen to today's class, then definitely everybody will be able to. Number 6 is the new that I have not covered in the last class. I mean, in the lecture, or I did not do. Today I will be discussing a similar problem and I will discuss extensively. And then after today's class, you should be able to solve all the problems. So is this fine?
yeah, I'll see if it helps after today's class.
Yes, yeah. And then everybody, as I mentioned in the email, I have created a Dropbox. I think you might have noticed. So when uploading the homework, like first you will be solving on your paper, right? A piece of paper. And then for example, there are 6 problems. You might need 6 pieces of paper or more than 6 paper. But then you scan and make PDF file and make a single PDF file. I mean, for example, you have 6 problem, so don't upload like 6 PDF files. Yeah, combine them into a single file. Do you understand what I mean? So
Yes.
yes. So when you will be scanning, so for example, problem 1, it took 1 page or it took 2 page, then that is your own file. So you save on your computer or whatever cell phone, but when uploading, combine them together. And then you upload that combined file, and then please don't upload the zip file, because if you upload the zip file again, I need to unzip and then see that on. So please use the PDF file and then single file. Okay, and then once you all will submit, I will be looking and my grading, and then I will be discussing. So sometimes next week I'll be discussing the solution. First, I will be discussing what are the solutions, right answer, and then I will be sharing you the graded homework so you all can see. Okay, let's stop sharing this on and start another one. Okay, now everybody, can you see the class lecture content?
Yeah, sure can.
Okay, great. Uh, So you all know that until last class, we covered three-phase circuit, balanced system, unbalanced system, and then followed by some numerical example. Uh, in case of delta system, what was the relationship of phase voltage, line voltage, or phase current, line current? Same thing in case of Y or star circuit. What's the relationship between line voltage and phase voltage, line current, phase current? We all discuss. Now we are continuing. So everybody say what I wrote at the top, the sum of the line voltage is 0 for a balanced system. that is VA plus VB plus BC equal to 0. So this means that if it is a balanced or symmetrical system, then the sum of, vector sum of all three voltage should be 0. So for example, you yourself can try that at home at your node. For example, F phase, it has 0 phase angle, then B phase minus 120 degree, C phase plus 120 degree. Then if you just sum up, like one at an angle of 0 plus one at an angle of minus 120 plus one at an angle of plus 120, you should get 0 if you use rectangular to polar, polar to rectangular conversion. So that is the meaning. So therefore, everybody, you will keep in mind, if it balanced system. Now, if it unbalanced system, then their sum will not be 0. You will get some value. And that is like detrimental. That has negative impact on the system. So we will be discussing, extensively today. And then similarly, IA plus IB plus IC 0. Because there's VA, VB, BC is for a balanced system that we are talking. So similarly, three line currents or three phase current, their sum, in this case, this is vector sum, this is phasor sum. Keep in mind, phasor sum, not the magnitude only, together with the angle. So phasor or vector sum should be 0. So therefore, if this is true that IA plus IB plus IC equals to 0, so therefore I have written the neutral conductor does not carry any current. That is, IN is 0 if the source and load are both balanced. But for an unbalanced system, current flows through the neutral conductor. That is, IN not equal to 0. So this means, so let's go back, explain. Can you see my whiteboard?
Yes, we can see it.
Okay, so therefore what I'm telling, for example, this is on phase, this is other phase, this is other phase. This is Y connected system. This is A, this is B, and this is C. And then this point is the neutral point, and this is the neutral line that is going. So this is the ion current direction. So what we are telling that if it is a balanced system, then there should not be any current flowing through this neutral line. Ion should be 0 in case of a balanced system. But once it is unbalanced, for example, we are talking, this is IA, and then this is IB, and then this is IC. Just an example that, okay, it has 10 ampere, at an angle of 0 degree, just an example. And then it has that 5 ampere. Like angle could be properly minus 120 degree. But then again, for example, it may have the equal amount and then plus 120 degree. So you see, this is the example of unbalanced system. Because here in this case, that for example, current is entering, just an example. So all three phase currents are entering here, and then current is going through the neutral line. But in that case, that will not be 0 because it is unbalanced system. Therefore, really in your calculator, you sum up these three, 10 at an angle of 0 plus 5 at an angle of minus 120 plus 10 at an angle, you would get some value. That will not give you the 0. But on the other hand, if you do these things, for example, it is not 5. It is that number. It is 10. Now you sum up these three, this on plus this on plus this on, you should be getting 0. At that time, it is not 0. So do you understand what I mean?
Yeah, definitely.
Yes. So and that is the negative side of the unbalanced system. That's why unbalanced system is not desired, because when it is unbalanced, because you see that current is no more, current is no more zero through the neutral. Now it depends on the magnitude. For example, originally the power operator or system operator has made this neutral line to carry 15 ampere, just an example, but you got like 20 ampere. So therefore this neutral line might be overloaded and might be burnt out, might be fully cut. So this means that this three-phase system does not have any neutral line. So that's the full safety issue. Or even though it might not be burnt out, assume that it did not get burnt, but because current is flowing, for example, some current is flowing, 15 ampere is flowing through this line. And then because this is neutral line, say there is another system, you don't know what is the system. This is a three-phase system and it has the neutral line. This is its neutral line. And this system and this system is nearby, for example, very close. What would happen? Initially, this system was pretty good condition. It has no current flowing through it. I mean, neutral current or zero in this system. But because this one and this one are neighbor, so therefore this current will try to enter to this neutral. And then this device will be heated up. And then, for example, at some point, they are like grounded. Like this system and this three-phase system was grounded at some point. This was the neutral line of this system. And this system has been, there was no issue with this system initially. There was issue only with this system, unbalanced. Consequently, current was flowing and that current will enter into the other device. And for example, you are the owner of this device, you might see that this device is gradually getting heated up. So you don't know the reason what happened. It looks like everything is fine in your home or in your system, but it is getting heated up. That could be the cause, that because your neutral and other neutral, they are bonded together and grounded together. It is never. And then, for example, you are here, you are standing here, or you are sitting here, just an example, and you are barefooted. And this is a, for example, land or soil. So you might get shocked because properly current is flowing through you to this neutral. Everybody, could you understand? Could you follow me?
Yes, yes.
Yes, this is great. Like everybody will remember, this is the negative impact or adverse impact of being an unbalanced system. Anywhere. The same thing, it could be true. For example, issue is not in this system, issue is in your system. For example, your system is also three-phase. Just an example, A phase, B phase, C phase, and this is neutral. And your system has been unbalanced. So through the neutral conductor, current will flow and it might flow in this direction. And then in that time, your system was fine. Initially, you have zero current, but from this side, some current might flow and enter to your neutral, and these coils will be heated up. At some point, you might feel that your system is, you don't know the reason. It looks like your system is fine, but your neighbor caused the problem. Sometimes that happens also. Okay. So then let's go back to that point. Yes. So therefore, this is very important. Okay. So now moving forward, I will be talking much more and you will be understanding a lot about the unbalanced system. It's pretty interesting. Now, everybody see this on phase sequence, and I have written positive and negative, although there will be another one like zero sequence. You see, I have written in this bullet here, zero sequence. Uh, and then this thing will help you a lot to solve the numerical problem in the homework. Uh, what I have written, phase sequence means what is the sequence of FH, BH, CH. So everybody see, if you see this left side figure, if you see this one, this is VN, this is VBN, then this is VCN. So what I have said ABC or positive sequence. Here what I have said, ACB or negative sequence. Everybody see? AN here, but then CN is here, then BN is here. I mean, both system is properly maintaining 120, 120, 120. That is fine. But see the difference here, A, V, C. But here, A, C, B. So similarly, so in real practice, if you see oscilloscope in both system, you see I have written phase sequence like A, B, C. So everybody see, this is a phase, and then after 120, the peak of B phase is coming, then another 120 C phase peak is coming. But look the bottom one, it is ACB. This is A peak, then C peak, then B peak. So see the difference. This is like the opposite of the different. So therefore, in United States, this is the sequence, positive sequence, ABC. And in some other country, this is the ACB system. I mean, in most of the countries, including United States, it is the ABC or the positive sequence, but some country has ACB sequence. Now, what does that mean? For example, you purchased a device from other country that has ACB sequence. For example, you purchase a motor, and your system here in the United States, you have ABC. So you have 3 point, and you want to plug in this system or this device into your system, there will be unbalanced because of the phase sequence. It is not properly matching. FH is matching with FH, but in United States, this is the B phase minus 120, but in the device that you purchase from foreign country or other country, it has C phase here. So then that will create problem. There will be some circulating current flow, and then either your system or that device might be burnt out and maybe damaged.
Can I
So
ask?
sure.
So I think I understand the clockwise rotation for the ABC sequence. Could the omega is drawn in the arrow is drawn counterclockwise on that? Could you explain that?
So it is just showing that you see, like for example, see the ABC like 0 degree, then minus 120, but then C phase is like clockwise, it is minus 240, right? Clockwise. But then that omega, if you go anti-clockwise, then that will be plus 120. That is the meaning of this direction.
Okay.
So that, do you understand? Yeah.
I think so.
Yeah. In case of the ACB, first A, then minus 120 C, then another minus 120 B. This means the B phase minus 240. But then if you go anti-clockwise, that is the direction of omega. If you go anti-clockwise, then B phase is plus 120. So that's the difference. I mean, in this case, ABC, B phase is minus 120, but in this system, B phase is plus 120. For ABC sequence, the C phase is plus 120, but ACB, C phase is minus 120. So therefore, omega is just indicating the counterclockwise angle direction. So, and as I told you, this is the real practice. Okay. Same thing, when you will be working in the lab, I think lab number 3 or 4 is still, I think you did not go to the lab. Hopefully next week you will be going for the orientation class, and then another week later, your actual lab will start. So experiment number 3 or 4, you have to start a 3-phase induction motor. So that time you will get the significance of the phase sequence. Just let me explain. This is pretty interesting. Okay, let me erase all of these things. Okay, so sorry. Okay, for example, okay, this is the motor. This is the motor. For example, this is A phase, this is B phase, this is C phase. This is the motor, for example, and you want to start it. This is the shaft of the motor. Now, for example, this is the indicated direction, the clockwise direction for this motor. Now, in the lab, you have this type of line. This is line 1, this is line 2, and this is line 3. So this thing is available in the lab, or this is your system, for example, 3-phase system. And this is the motor, induction motor. It has A phase, B phase, C phase, and this is the indicated direction. This means if it rotates opposite direction, then that is the wrong direction. This is the indicated direction. Now everybody see, for example, you are making connection to the motor. You made connection in that way. And then at first you notice that motor has started rotating in the opposite direction. This is the indication that the phase sequence has not been matched. Phase sequence is different. But if you see that, okay, after making this connection, it is properly rotating in the suggested direction or recommended direction, then it is fine. It properly matched. If you see that no, it is rotating other side, opposite direction, then immediately you stop the motor. For example, immediately you disconnect all the connection, and then motor will be stopped. And then what you will be doing, you will be just swiping two lines. You will make connection this on here, and you might make connection this on there, and then this one. The next time if you start the motor, then you will see it is properly rotating in the suggested or the given direction. I mean, you just need to swipe, interchange any of the two lines. Then that will like, fix the phase sequence issue, and properly motor will indicate in the suggested direction. So everybody, could you just follow me the importance of the phase sequence? So therefore, this thing, I mean, you might notice in the lab number 3 or lab number 4, probably lab number 3, that at your first attempt, when you are making connection, motor may not rotate at the indicated direction or recommended direction. At that time, immediately shut down the system and then just swipe or interchange any of the two lines. Or if you keep connection here, then connect L2 line with C and L3 line with B. So just interchange any of the two lines. That will fix the phase sequence. And then you will find that, okay, motor is rotating in the suggested or the actual direction. Okay. Okay, so everybody see, so we were discussing this one. So now couple of the thing, with the help of symmetrical component tool, an unbalanced three-phase system can be decomposed into three-phase balance system having positive, negative, and zero sequence. Now, these are the definition. You see, I have written here balanced three-phase voltage. So this phase sequence, positive or negative, this is the case of balanced system. Now, for example, there is an unbalanced system. So in case of unbalanced three-phase system, how you can analyze the phase sequence? So I have written that there is a tool or methodology. It is called symmetrical component tool. Like if you Google, then you will find this one. What is the function of that? It analyzes a unbalanced system. It decomposes, it divides an unbalanced three-phase system into three-phase balanced system having positive, negative, and zero sequence. So therefore, and then what I have written, with respect to positive sequence, negative and zero sequences are not desired. And during any unbalanced fault, current flows through the neutral line of Y-connected system. So we already discussed. And then, so I will be explaining you what is the negative sequence and zero sequence, positive sequence in case of unbalanced three-phase system. And you see the tool is symmetrical component tool. Then once again, let me take you to that whiteboard, and then you will get fun there. So let me read it. Okay, so therefore, everybody, see, for example, this is VA, and then this is VB, and then this is VC. Sorry. And then this is VC. So everybody assume that this is VA, VB, and BC, this three-phase system. This is a three-phase system, but unbalanced system. But their phase sequences, everybody remember, phase sequences ABC. This means this is the positive phase sequence. So this VA, VB, BC are unbalanced system, but their phase sequence is ABC. Now we want to analyze this unbalanced system with the help of symmetrical component tool, and I want to convert each of them into three-phase balance system. So now everybody see what I am doing. VA1 plus VA2 plus VA0. So this means I decompose this phase or F phase into three components, VA1, VA2 plus VA0. So I am coming that point. So similarly, I am decomposing VB into three parts. VB1 plus VB2 plus VB0. I mean, see the pattern, the way I am making, like 0, 0 here, 2, 2 here, 1, 1 here. Just it is B phase, V, B, B, here it was A, A, A. Similarly, decompose C into three component, C1, and then VC2, then plus VC0. This means that again, everybody, what I am doing, originally this VA, VB, BC was three-phase unbalanced system, but their phase sequence was ABC. Now I decomposed each phase into three parts with like 1, 2, 0. I mean, there is significance of this number. Similarly, B phase. Now everybody see, can you see that this set, everybody see this set, VA1, VB1, VC1. Now see this one, VA2, VB2, VC2. This is another group. And see the third set, VA0, VB0, VC0. So therefore, this when it goes the symbol 1, 1, 1, and you see it has been a three-phase system, VA1, VB1, VC1. So this is the positive sequence. And then this one, VA2, VB2, VC2, if you see the letter 2, 2, 2, this is the negative phase sequence. And this one, 0, 0, 0, this is called the zero sequence. This means that although this is F phase, B phase, C phase, they are in zero sequence. They don't have any phase difference. For example, this is VA0, then on the same line, this VB0, on the same line, the VC0. That's why it is called zero sequence. But you know, now come back to the original, VA, VB, BC. I said their phase sequence was ABC. This means this is A, this was B, this was C. Now look, this set, what I said, the positive sequence set V1, VB1, VC1. This means that this is now the balance system. This is also balance system. This is also balance system. All three, column, all three sets are balance system. The three-phase system. But this positive set has the positive sequence, and it has the same sequence as the original three-phase unbalanced system. This means in this case, for this set, this is the sequence. This is A, this is B, this is C. The middle set, 2, 2, 2, this is three-phase balanced system, but the phase sequence is ACB. This is A, this is C, and then this is the B. And then, as I said, the 0, so you don't need to draw. This is, all in the same line. It has 0 phase difference. Accordingly, it is called the 0 sequence. So therefore, everybody, then once again, originally at the leftmost side, I had a three-phase unbalanced system, VA, VB, VC. That has the phase sequence ABC. This one. Now, because this is unbalanced system, with the help of that symmetrical component, we decomposed each phase into three-phase system. And then now they are making a good sequence. Each phase, each set has created a balanced three-phase system, but they have different sequence. Like this set with 1, 1, 1, ABC. This means this phase sequence, this is balanced system now, but each phase sequence is exactly the same as the original unbalanced system. This is the second set. It is called the negative sequence because its phase sequence is ACB, not ABC. This is the third set. Therefore, what I want to tell you that this was three-phase unbalanced system, and I got three new balanced system. This is one set, other set, this is other set, although they have the different phase sequence. But what is the significance of this one, negative and the 0? So you see, these two looks like the additional component. These two are not desired component. It was unbalanced system, that is fine, and this is three-phase, A, B, C phase, and I got on positive sequence three-phase system. But what is the meaning of this negative and 0? Those two will have negative impact on the system. Like that negative sequence, this will cause some sort of heating in the system, and then 0 sequence, this is also will cause heating, and the 0 sequence current, this will flow through the neutral of the Y connected system. And even though it is not Y connected system, it could be delta connected system, but still this 0 sequence component current will flow through each coil of the delta system. Consequently, over the time, the coils will be overheated and may be damaged. So that's why with respect to positive sequence, negative sequence, and 0 sequence are not desired. So therefore, this is pretty interesting. I'm just telling you the significance of the phase sequence and how we can analyze an unbalanced system. So everybody, could you follow what I said here?
Yes, I think so.
Oh,
Yeah, not really sure where.
hello? Okay, so therefore, then now I'm going back to that slide again. Yes, I explained you this bullet. With the help of symmetrical component tool, an unbalanced three-phase system can be decomposed into three-phase balanced system having positive, negative, and 0 sequence. That is the thing I explained you through the whiteboard. And then especially everybody keep in mind that 0 sequence, that is the most detrimental, that is the most harmful for the system, because it is 0 sequence. Although they are not making ABC or ACB sequence, all three phases are on the same line. This means that if you have 0 sequence current, for example, IA plus IB plus IC, they have the equal magnitude, but they are getting 3 times. For example, 10, 10, 10, 30 ampere. And that 30 ampere zero sequence current will start flowing through the neutral in case of a Y connected system. In case of a delta connected system, there is no path, there is no neutral. So that 30 ampere will be divided, maybe equal or unequal values, but those will be blocked or trapped into 3 coils of the delta connected system. Consequently, those coils will also be overheated and at some point maybe burned. That's why zero sequence is very detrimental, very harmful for the system. And when you are getting this on, in case of unbalanced system. That's why, I mean, in any case, unbalanced system is not helpful. It is all like the negative. It has disadvantage. It has the lots of the drawbacks. That is the meaning. Now, moving forward, one important thing like power factor correction or improvement. So everybody see in the homework set, the last problem number 6. So from now on, everybody please listen to me carefully. And you see here, I will be solving on a problem, example 2.8, and then you will be able to solve that problem number 6. And I believe you all will be able to solve 1 through 5, like after today's class. What I have written here, you see, what is the topic? Topic is power factor correction or power factor improvement. So you all know the power factor, and what I have written, power factor correction is needed to reduce system loss, increase efficiency, and to have better voltage regulation. And I said reactive power is of no use. It just causes heat and loss in the system. So therefore, you all know, at least from the circuit standpoint, that there are 3 types of power. One is called real power or active power. Other one is called reactive power, and then the apparent power. You remember that power triangle. But real power or active power, that is useful to us. For example, you are using a light, it has 60 watt or 100 watt. Or you are using a fan 40 watt, 60 watt. When the unit is watt, this means this is what you use. That is useful to you. But once it is reactive power like var, kilovar, megavar, or simply var, and the Q value, that is of no use at all. But it is present in the system. You can't avoid it. It just causes heat and loss in the system. And then that is the reason today we are discussing power factor correction. Because so now everybody, then 1 second, let's, and then it will be clear to you. 1 second, I want to take you to that whiteboard. Okay, so everybody see. So this is the theta. See, you all know this is phi, that is the real power. This axis is Q, and then this one is as apparent power. Like P squared plus Q squared. And everybody see cosine of theta, which is the power factor. P over S. And then let me write down the S here. S is that, sorry, root over P squared plus Q squared. I mean that I already wrote here. So everybody say this is our definition. This is the power factor. We are discussing power factor correction. We are discussing the significance of low or the high value of the power factor. So everybody look, that is the thing I am telling, that this is the P, this is in watt, this is useful to us. This is Q, this is called the reactive volt ampere. This is of no use at all. In our real life, this is of no use. It does not help at all. It only creates heating and loss in the system. But you can, then you might argue that no, I will not be using this one. But you can't avoid it. From the system, automatically, inherently, it is being generated. Like you remember, I was telling you, for example, in a power plant, this is the three-phase system, but there are three-phase coil. There are three-phase coil. From where you are generating voltage, you are getting the voltage from this coil. So what is a coil? Is it resistor or capacitor? It's an inductor, right? So you all know. So and then if it's inductor, then you see this will cause the reactive power, QL. Like when it is capacitor, it will cause capacitive reactive power, QC. When it is resistance, then you will get the real power, which is the Phi. Like Phi equal to I square R. That is this watt. But you see this L, this is this Q. Now this is QC, this is also the var, unit is the same, this is reactive power, but this will help you. This is helpful for us. This is not helpful for us. So everybody, I mean, keep in mind the difference between R, L, and C. This is the power. A resistor can consume power. This is helpful for us because we can utilize that power. L and C both will cause power. Both are the reactive power. I mean, this on this Q. But this will be helpful, but this will be not helpful. This is of no use at all. It just causes heating in the system. But then why are we discussing? As I told you, in the power plant, originally, voltage is built up with the health of coil. And this coil is this coil. So although it is providing, I mean, some real power, but simultaneously, it is causing some reactive power. That's, and as I told you, this does not help us. It just causes heating and it is naturally being developed. So we have to try to compensate this on. We have to try to minimize the value of K. You can't avoid it because it is coming from the system. Even not just generator, along the line, those cables, those are basically the inductor, mainly the inductor. It has little resistance. In the transformer, think about the transformer. That is basically the coil, magnetic coil, primary side, secondary side. In our real life, many loads are based on the Q. In industry, most of the loads are based on the Q. So therefore, while we use the loads, we have to use the loads, but unfortunately, because there is coil, so that will cause some Q. And you have to fight against the Q. You can't avoid it. You have to allow you in the system, but then you have to put means, you have to put control means to minimize its negative effect. That is the topic, power factor correction. So this means everybody see, just now look, this concentrate this triangle. And if you see this thing, the definition power factor cos theta. So power factor improvement meant try to make the cos theta value to be 1. So you all know what is the maximum value of cos theta. If you can make theta value 0 degree, only then like cos theta will be 1. So this means everybody look in this figure, how you can make the cos theta 0? If you assume the Q is 0. If you can make Q value 0, you see, then this will come down. So this hypotenuse, S line will fully superimpose on this line. Then you see the definition, cos theta is P over S. This means P over P or S over S, that will be 1. So this means power factor improvement, power factor correction means trying to make the power factor 1. But in real practice, you can never ever make the power factor 1. it can go close by, like you can make 0.98, 0.97, 0.99. In real life, never ever it is 1, but that should be your target. Try to achieve power factor close to 1. And if you see this diagram, what is the way? Only way, if you can squeeze this on, reduce, 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 and if you can make it fully 0, this Q value, only then the cos theta will be 1, power factor will be 1. I mean, and then everybody, what is the significance of this one? You see, because phi equal to this real power, VI cosine of theta for single phase system. In case of 3-phase system, it will be multiplied by √3. So everybody see, you are calculating phi VI cos theta. So whatever your voltage current is, it is dependent on power factor. Now, for example, if you get here 0.5, then your value is getting, power value is getting half. If it is 0.2, again reduce. If it is 0.1, again 10 times decrease. So on the other hand, if you can increase in this way, and if you can make cos theta value is 1 or close to 1, that time you are getting the highest power, this power in watt, because that is useful in real life. So Q is not useful in real life. It will just cause heating in the system. So if everybody, could you follow me what I am explaining?
Yeah, sure can.
Yes. So therefore, what I am telling that based on this, what is the way to achieve the power factor close to 1? Only way that if you can reduce the magnitude of Q. For example, you reduce. If you can come down until that point, for example, only this portion. So maybe theta is only 5 degree, 10 degree. That will be close to 1. That is also great. Now the question is, how you can reduce the value of Q? Or what is the way? What is the element? What is the component that can reduce Q? That is the capacitor. That is the capacitor. Therefore, just let me clean up this one. So for example, everybody see, you have a series circuit, and you have R, you have L, and you have C. Then what, this is R, this is L, this is C. Everybody go back to the circuit knowledge. What is the impedance? R plus J XL minus XA. Everybody, can you remember this one? The impedance for this one.
Yeah, sure do.
Yes. So therefore, look this one. This is R. You know that this P watt is related to R. So look this component. So therefore, for example, let's say resultant is X. So therefore, this is XL, but this is minus XC. This means if both becomes equal, XL equal to XC, then this thing will be cancelled. So your circuit will be Z equal to R. So and then that is the definition of cos theta as well. If you see this triangle, like impedance triangle, this is G, this one is R, and this one is X, and this one is the theta. So therefore, look this one. In this case also, cosine of theta, which is the power factor, this is R over J, right? So based on this triangle, this is R, this is X, and this is J, because J equal to root over R square plus X square. So this is also the definition of the power factor, and you will get the same result by using this method and by using this method. So this means that if you can cancel out the impact of XL, it is plus JXL, but minus JXA. By putting the capacitor, can cancel or compensate the negative impact of L. So if you can make like Z equal to R, therefore in this equation, because R equal to J, cos theta will be 1. So therefore, what we are discussing, what is the way to reduce the magnitude of the Q? Only try to compensate or minimize, or if possible, fully nullify the effect of the L. So that's why the method or to improve the power factor is the capacitor. So capacitor will help you. Capacitor also provides the reactive power, but it is against the inductor. You see, because of this sign. Therefore, if you say this is the positive reactive power, then this is negative reactive power. This means this negative reactive power will fight against the positive reactive power. Therefore, when I'm talking in this figure that, okay, if I can reduce the magnitude of K, this means that only if you can insert capacitor in the circuit, so that will work in this direction, and then this will, this magnitude will come down. And then if you can make, for example, theta is only 10 degree here or 5 degree here, or if possible, fully nullify it, make it this, then you know this hypotenuse will like fully superimpose on this line. So that is the way to improve the power factor. And then also say, I mean, what is the, how it is impacts the system efficiency, how it impacts the voltage regulation, how it impacts the voltage drop. So look, another explanation. Let me erase this side. Okay. Everybody see my equation. Everybody please look. For example, that equation I wrote, P equal to VI cosine theta. So from here, I want to derive the I. So what is the I value? So I value would be phi over V cosine theta. Okay. So now I'm trying to explain you how the Q impacts us. So with the help of this equation. So I'm finding the value of I, phi over V cos theta. So assume that for a given system, your power is fixed, your voltage is fixed. You see that, you know that in real life, voltage does not change that much unless there is an issue with the system or unless the unbalanced happen. Voltage is pretty much the same at your home. It is 120 volt for single phase system. So I am assuming that for a given system, voltage constant, power constant. Now, what is the impact of power factor on the system? And you see, this power factor is related to that actually the Q, as I was calculating the theta. So everybody see, for example, your cos theta value is, for example, cos theta value is 0.1, just an example. Then you will get some current value, right? And then you gradually increase. You put 0.2, then you will get lower current value. In that way, if you just increase, if you go in this way, when cos theta value is 1, for example, only then you will get a smaller current. So do you understand what I am explaining? I am explaining that when this cos theta or power factor value is low, low means, for example, close to 0, 0.01 or 0.1, that time you will get higher current. And as you go upward, if you, if you increase the cos theta value upward until 1, then your current value is decreasing. So this means that when the power factor is very low, very poor, that time current value is high. So come back to this diagram. So if you have a very Q value, meaning that this is your theta, so cos theta is P over S, you are getting higher value of theta. In that case, your power factor value will be very, very low. And then if you try to increase the power factor value, your current value will be decreased. Now, what is the impact? So come back here. Look the current in this circuit. Everybody see, when 10 ampere was flowing, just an example, so you will get like I squared R, the power value, or I square XL, or I square XA. On the other hand, for example, current value is much low. So this means your loss will be much lower. And your voltage drop, like from this point to this point, if you have higher current, then you will have higher voltage drop. So you will get much lower voltage here. On the other hand, if your I value is small, then there will not be much difference between the voltage here and here. So, and then this means that if your power factor value is low, in other words, your Q value is high, then you will get higher current. That will cause higher loss, higher voltage drop, and much more loss mean system will be less efficient. Those are the negative effect of the Q. And you see I square R loss, if I value is higher, that will cause loss, and that loss will ultimately nothing but the heating. That's why I said that much more Q in the system means much more loss, much more heating in the system. Everybody, could you understand what I explained? I mean, I am explaining why do you need to improve the power factor? Why the lower power factor value is not helpful? Why it has the negative impact? So with the help of this equation, you can understand that lower power factor value means higher value of current, and higher value of current means higher loss, higher voltage drop. Voltage will be significantly drop at each and every point. Consequently, your system will be lossy, system will be inefficient. That is the meaning. That's why we have to improve the power factor. So now come back to that slide again. Everybody now see, read. Power factor correction or power factor is needed to reduce system loss, increase efficiency, and to have better voltage regulation. Voltage regulation means there should not be much difference between 2 points, I mean, in a series circuit. If there is much higher voltage drop, then that is called the poor voltage regulation. But we want to achieve higher or better voltage regulation. And then reactive power is of no use. It just causes heating and loss in the system. And power factor can be improved by inserting a capacitor in the circuit. That's why from today, you will be asked these questions in your FE exam. What is the way to improve the power factor? A straightforward you answer by inserting a capacitor in the circuit. Now, at this level, at the undergraduate level, you are fine with this answer. But if you go graduate level, this answer is not enough. There are some other sophisticated or robust power electronics component like static Bard compensator, SVC, or STATCOM, static synchronous compensator. There are some sophisticated power electronic equipment that can play the same role. I mean, those devices are used to improve the power factor. But at your current level, you just remember this thing, that capacitor can improve the power factor. Now, by utilizing this concept, everybody now concentrate. I will be solving this numerical example, and that will help you to solve your homework problem number 6. I mean, very similar. So everybody, please have a look. What's the statement? Assume that a 2.4 kV single phase circuit supplies a load of 294 kilowatt at lagging power factor, and that the load current is 175 ampere. To improve the power factor, determine the following. First question, what was the uncorrected power factor and reactive load? The second question is new corrected power factor after installing a shunt capacitor unit with a rating of 200 kilowatt. So everybody understand the problem. You have a single phase system. This is your load, 294 kilowatt. This means this is the P value, real power value. And this is the voltage. And clearly it says it has the lagging power factor. And then the current value is on 75. So for this system, what was the power factor, uncorrected power factor? Because as I told you that, I mean, the goal of this problem to improve the power factor. So what was the unimproved, or before making correction, what was the power factor value? and what was the Q value. Reactive load means what was the Q value. And then you will find some power factor value, which will be definitely much lower than 1, maybe 0.7, 0.6, or not more than 0.8. And then we have to improve it, or we have to correct it. So what should be the new corrected power factor? And as we discussed, capacitor can improve the power factor. Assume that we have installed a shunt capacitor and the capacitor rating is 200 kilowatt, means it reactive power. Then what? So therefore, everybody look the solution. I think that is here. Everybody, can you see? So first, everybody see, at first I am writing down phi equal to vi cosine theta, because this is single phase system. If it would be 3-phase system, I would write phi √3 VL cosine theta. Could you follow me what I am telling?
Yes.
Yes. So therefore, because you are assigned the homework, especially problem number 1 through 5, mostly those are the 3-phase system. So many times you might need to write phi equal to √3 VL cosine theta. But now I am discussing single phase system. And I think homework problem number 6 is also about the single phase system. Therefore, everybody please look this problem carefully. So first I wrote the single phase equation, and there 294, this was my power value. You see, this value was here, the 294 kilowatt. Look the problem. And remember, this is the voltage and this is the current value. So I substitute in that equation 294 kilowatt, 2.4 kV, I value was 175 cosine theta. That is my interested. I am interested to find out the cos theta. That is the power factor. So everybody see, if I have done correctly, then 0.7. So you see, the power factor is fairly low as compared to 1. Like as I told you, the desired power factor should be 1, but in real practice not possible. So we should try to go as close as the 1, but we got 0.7. That is the answer to the first question, uncorrected power factor. Uncorrected means still we did not put any compensator. We did not put any capacitor or any other means. That's why it is called unimproved or uncorrected power factor. And the question was, second question was, what is the reactive load? Uncorrected power factor and reactive load. So everybody see, as I told you, reactive load means reactive power, VI sine theta. Everybody remember your circuit knowledge? We discussed, or even in the previous class, we discussed reactive load, VI sine theta. So you need sine theta here. That's why from here I derived sine theta. Everybody see? This was the cosine theta, and then find out the theta by cos inverse, and then get it sine theta. It is 0.714 about approximately. So I substitute that value, and then V and I as it is, similar to the previous step. So I got about 300 kilowatt. Like I got 299.99. So I just approximated it is 300 kilowatt. Now, what was the main question? Everybody see, this was the main question. What should be the new corrected power factor after installing a shunt capacitor unit with the rating of 200 kilowatt? Now you have inserted a capacitor. That's why you see, I have drawn that power triangle that I was discussing with you a few minutes back through the whiteboard. This is P, that value 294 kilowatt that I used here. This axis was Q. So what was my Q? Original Q, Lucy, from here to here, that is 300 kilowatt. Where I got that? I got from here. Okay. And then there was one theta. I have designated theta volt. Everybody say, I have designated by theta volt. Theta volt mean the old value or the previous value with respect to this original triangle. And this was the full Q value. Now, how much capacitor is providing? Capacitor is providing, you see here, as I showed you, capacitor is providing a 200 kilowatt. Look the statement after installing a shunt capacitor. So once you insert the 200 kilowatt, so that I am saying from top to until this point, just by hand I drawn. It could be a little bit down or little bit up, that's fine. So this is 200 kilowatt. This means capacitor reduced the magnitude of Q. So then now you got this triangle, new triangle, everybody's, this page same, this is your new Q. So I have given the new QT, this magnitude, and then this is the hypotenuse. So you are getting a new theta. So that's I have designated theta nu. So the original on the previous one or theta old, and I have got the new theta. This is theta nu. And I said this QT is 100. How I got that? From here to here, it was 300 kilowatt, this value. Capacitor provided 200 kilowatt from here to here. Therefore, remaining is 300 minus 200. So 100 kilowatt. Now everybody concentrate only on this new triangle, new small triangle, this one. Because this is my new triangle. My P value is the same as the previous one, but I have the new Q, which is the 100. Now my goal is to find out the power factor. So what I am doing, tangent theta nu. Everybody say tangent theta nu with respect to this one. First, I want to find out what is the theta nu. And why I am doing tangent? Because I know the phi, I know the Q value. I don't know what is the S. So that's why I am taking the help of P and the Q. So everybody say tangent theta is this one, perpendicular over base. So QT over P. What is QT? 100 kilowatt. I just converted into watt and phi value was 294 kilowatt. I converted into watt. So I got 0.34. So what is the theta nu? Tan inverse of that, 18.78 degree. So what is the new corrected power factor? Cosine theta nu, cosine of that value. You see, now I got 0.95. So therefore, see the difference? Initially it was uncorrected power factor of 0.7. And now I got improved value or corrected value, which is 0.95. Everybody, could you follow this one?
Yes.
Oh, great. So therefore now, if you see the homework problem number 6, you will be fully fine. But there is one thing. I think in homework problem number 6, you are asked to find out the capacitor value. Now I am helping you to do that, how to do that. So everybody say, in this case, the capacitor value was given in terms of kilowatt. But the homework problem number asks, what is the value of capacitor in farad or microfarad that is needed to improve a power factor value? So in the problem, the power factor, improved power factor value was given. I mean, a little bit that one is tricky. So I think this value and this value was given in the problem. And then you are asked to find out what is the capacitor value in farad. So therefore, at that time, to solve that, what you would be doing, I'm giving you the hints for problem number 6. Okay, so, okay, here is my eraser. Okay, this is fine. So once you get that capacitor value, once you are able to get that capacitor value, you can write Q say VC square over XC. Does this make sense? For example, because you are inserting a capacitor to improve the power factor, this is capacitor. What is the voltage across the capacitor? For example, that is VC. And if you know what is the QC, reactive power, this means this amount, you know, with the help of capacitor that was showing in the previous problem, this is Q. This is QT. And then this amount from here to here, this was the QC that we showed in the previous problem. So once you are able to find out that value, what was the value of the QC, the problem that I discussed just now, the QC value was given. But in the homework problem, at first you have to find out the QC value with the help of this type of triangle. And then once you find out, after that, please use this equation. Everybody listen, QC, VC square over X. Because the question is to find out the C value. What was the capacitor value? So therefore, how you do that? Once you write down this equation, and what is the VC value? You know the terminal voltage was given in the problem. Use that value, that one. Q value you got. For example, you got 100 kilowatt, just an example. Your VC is like 100 watt, and that is squared. Then you calculate the XC. And once you calculate the XC, let me erase this thing. Once you calculate the XC, what is XC? XC is 1 over omega C. And what is omega C? Omega? 2 pi f. That is the omega. So therefore you see, from this on, with the help of QC, VC value, you will be getting XC value. Then use this equation. You plug in XC value here, and 1 over omega C, 2 pi f. Frequency was given in the problem, probably 60 hertz. You put that value. You know the pi value, so you will be getting the C value, either in farad or microfarad, whatever it is. So that what you are asked in problem number 6 in the homework set. Everybody, is this fine? So therefore, I discussed what you need to find out the capacitor for the homework problem number 6. So you need to exactly follow these steps to calculate the capacitance value. So keep in mind these things. Okay, I saved it. Let me stop sharing. So I am going back again. Okay, so therefore, first everybody once again after the class, please understand this problem once again. Try to understand this triangle and then jump into that problem number 6. Okay, so then I have a little more things and then we will conclude for today. Here you see what is the topic. Topic is 2 wattmeter method for 3-phase power measurement. Meaning that I want to measure 3-phase power with the help of 2 wattmeter. So you all know that wattmeter can measure the power. For example, you have a coil and you want to measure the power. So and you know wattmeter has 2 coils, potential coil or voltage coil and current coil. Voltage coil measures the voltage, current coil measures the current. So the multiplication of voltage and current will give you the power. But you might think that because this is 3-phase system, you might need 3 wattmeter. No, with the help of only 2 wattmeter, you can measure the 3-phase power. That's the interesting thing. So you see what I have written? To measure the power in a 3-phase circuit load, it is conceivable that a wattmeter can be connected to measure the power in a single phase, and this quantity can be multiplied by 3. Now you might argue that no, I will not be using the even 2 wattmeter. I want to use only 1 wattmeter because 3-phase system, it has 3 phase, A phase, B phase, C phase. First I will measure the 1-phase power and I will straightforward multiply by 3. But what I have written, you see, in most practical circuit, however, it is impossible to connect a wattmeter in this manner. You know, for the single phase system, to measure the power, of course, you need the neutral line also. Therefore, once again, let me take you there. Just a little bit. Let me erase these things. Okay, now for example, you have a, three-phase system. And then this is other. For example, this is Y connected system. Just an example. And then this is the neutral point. So this is the neutral line. And for example, this is F edge, this is B edge, this is C edge, and this is the neutral line. Now, you know for example, you have one wattmeter. Wattmeter, the wattmeter has two things. One is called the current coil, and other thing is called the potential coil. This is called CC, this is called VC. Potential, the potential means the voltage. It is the same thing. Potential coil, current coil. This coil measures the current. This coil measures the voltage. So the multiplication of voltage and current gives you the power. So this is called the wattmeter. So now, for example, you have a three-phase system and you have one single phase wattmeter in hand. So therefore, I am connecting the wattmeter. This is PC, and then because to measure the voltage you need 2 points, this point, and then you need the help of neutral. So this is 1 wattmeter. So for example, you have only 1 wattmeter, you use that wattmeter and you measure the power here and then multiply by 3. So that's right, you will get the correct result. But the problem is that always the system might not be exposed in that way. You always might not see that, okay, you are getting the neutral line. So if you don't have the neutral line, for example, it is just this type of box. You are not looking inside. What is this? Only you can see there are 3 leads, 3-phase system, like F phase, B phase, C phase. Then how would you connect the wattmeter? Because this is F phase, B phase, C phase. You can't see the neutral and you don't know what's the internal construction. And you have one wattmeter, single phase. So therefore you see here I connected the potential coil, that means the voltage coil, on end is here, but other end with the neutral. Current coil is fine, it is in series. So you can connect the current coil here, but where you would connect this coil, potential coil, because this is B phase, this is not the neutral. So that's why it is always not possible that you can connect a single wattmeter through the neutral and you will get the value, and straightforward you would multiply by 3. It is not always possible. That is the meaning of that one. So now go back there. Now everybody come back. In most practical circuit, however, it is impossible to connect a wattmeter in this manner. In this manner means the way I showed you in the whiteboard. Consequently, a method called the 2 wattmeter method is generally used. And the connections for this method are shown in figure in the next slide. I am showing the picture. And the algebraic sum of the 2 wattmeter readings is the total 3-phase power. It can be shown that this method works for both balanced and unbalanced systems. So everybody see this diagram? Everybody look. This is a 3-phase coil. You don't take care about that H1 and H5, those numbers. This is like realistic coil. So that's why those numbers are given, those symbols are given. This is on coil, this is other coil, this is other coil. So this is the 3-phase system. This is C phase, this is B phase, and this is A phase. Now you want to measure 3-phase power of this system. So look the configuration. W1 means this is 1 wattmeter. W2, this is another wattmeter. And as you can see, I was telling you in the whiteboard, each wattmeter have 2 coils. One is measuring current, other coil is measuring the voltage. That's why it is called CC, current coil. This is called VC or the VC, voltage coil. Now look the configuration, and this is just on ammeter. It is measuring the current in this line. Everybody look the wattmeter on its connection. This is current coil with this phase, C phase, one end of the ammeter is, sorry, current coil is connected, other end is connected to this line. You know, this is three-phase system, so there are three lines, 1, 2, and 3. Voltage coil, look the connection. Voltage coil, one end is connected here, and then the other end is connected at this line, which is the B line. Now see the wattmeter 2. This is the current coil. So this is connected in this line in series, and it is going here. And then the other end of the voltage coil is connected here, and then the other end is common to this point. As you know that current coil is connected in series like this is, and in this case, like this is the series connection. But voltage coil, you must need 2 points. One is this point and other end is this point. In this case, one is this point, other end is this point. So this point is common to both wattmeter. That's why this means this system, these two wattmeters are including or taking into account this second line, the B phase, without having any coil connection there. Automatically that is included in these both wattmeter. That's why the watt, for example, you got this reading 100 watt and you got this is 120 watt. So this 100 plus 120. So total three-phase power is 220 watt. Now, if the neutral would be available for this system, and if you used only one single wattmeter and measure the power, and then you can measure 3 times or you multiply by 3, you would get the same reading as you are getting with the help of 2 meter. That's why simply you remember that with the help of 2 wattmeter, it is possible to measure the three-phase power. Just you look the reading, and in the first experiment, in the first lab, exactly you have to use this diagram, exactly. So everybody, that's how you keep in mind. I mean, still I did not upload all the labs. I mean, soon I will be uploading, hopefully this week. But the experiment number 1, you need to make this type of connection. Experiment 1 is related to three-phase circuit, balanced, unbalanced, those analysis, and you need to measure the power. So then please exactly use this configuration to measure the power. Is everybody fine? Okay, and then I have the last slide for today. Just some sample questions. I mean, with that, like we are concluding this chapter, three-phase circuit. Next class, I will be starting the transformer, both single phase and three-phase transformer. So here, like you might expect this type of short questions in the exams, in the midterm exam or the final exam. For example, what's the advantage of three-phase AC system over single-phase system? What's the disadvantage of an unbalanced system? Why is power factor improvement needed? How can the power factor be improved? Consider a series RLC circuit with the AC input voltage. Under what condition will the current be maximum in the circuit? So you all know the answer like from 1 through 4. So just let me discuss in a minute this one. You have a series RLC circuit with the AC input voltage. Under what condition will the current be maximum in the circuit? So therefore, just a minute, and then you all will get and you're fully fine. Let me erase all of these things. Okay, so for example, this is your voltage source. There is AC voltage. You have R, you have L, and you have C. And RLC. The current flowing, which is I. and this is the AC voltage. So the question number 5 was, what should be the condition that the current flow will be maximum in this circuit? So first of all, everybody, what is the current expression for this circuit? Current is that V, that voltage over G, impedance. So this means V over, what is the G? R squared plus you know that you all know that for this circuit that G, we already wrote that G is R plus J XL minus XC. So therefore this was in complex form, but here I am using the magnitude. That's why I did not write the J, because root over, I am taking its magnitude, root over R squared plus this squared. So everybody see, the question was for this circuit, or under what condition the current will be maximum. So what is the condition the current will be maximum? If, everybody see, if XL becomes equal to XC. Sorry. Everybody look the denominator. V is V, R is R. If you can cancel out, if you can make this portion 0, this means if XL equal to XC, then you are getting V over R. That is the maximum current. That's the question. So therefore your answer to that question would be, if we can nullify the inductive reactance, or in other words, if I can fully compensate the XL with the help of XC, only then Z value will be R and then current value will be maximum. So simply speaking, when XL equal to XC, inductive reactance equal to capacitive reactance, and then the circuit impedance will be low and current value will be maximum. Is everybody fine?
Yeah, we're good.
Yes, very good. Yeah. So therefore now I am stop sharing. I think that's all for today. So does anybody have any questions or anything? If no, then